In this video, I'm going to be talking about the Monty Hall problem, which is quite a famous problem. It's named this because it's similar or exactly the same as a problem which appeared in the game show Let's Make a Deal, hosted by Monty Hall. And here's what the problem is. So suppose you're in a room that has 3 doors, and behind one of the doors is a prize. Let's say that the prize is $1 million, and the other 2 doors lead to an empty room. So you want to select the door that has the prize. Now, the way the game works is first you select a door, then the host opens one of the other doors and shows you that it's empty. And this is always possible because there are two empty rooms, so even if you select an empty room, there's another empty door that can be opened. So you select a door, one of the other doors is opened and shown to be empty, and then you have the option to either stick with your original choice or switch to the other door which is not selected. And so you can imagine this playing out. Suppose there's money behind the second door, and then one way this could play out is you first select door 1, this is your selection, then the host opens door 3, and you know that room is empty, and then you have the choice to either stick with your original choice or switch to the second door. So in this case, switching would have been the right decision because that would get you the money. But in general, it's also true that it is a smarter strategy to switch every time. The probability of selecting the correct door at the beginning is 1 in 3 because there are 3 choices and only one of them is correct. What happens when one of the doors is opened after you've selected one of the doors is the probability. So at the beginning there's a 1/3 probability of each door, as far as you know, and you select one of those. Then, after knowing that one of the doors leads to an empty room, that 1/3 has to somehow be transferred to these because you know that the money is behind one of these doors. And as it turns out, the door you selected remains 1/3, and the other door becomes 2/3. And this is somewhat unintuitive, but I have a way of demonstrating this. And I think like the unintuitive part of it is specific to this being a 3-door problem. So I'm going to now walk you through what this looks like if you have many more doors and show you that it's really quite intuitive, that it makes more sense to switch. So suppose instead of there being 3 doors, there are actually 1,000 doors. So there's door 1 over here, and a whole lot of doors, and door 1,000 over here. So you have 1,000 choices at first. And so again, there's just one door that has the money, and there are 999 doors which are empty. So suppose now the way it works is you're supposed to select a door, then 998 doors are opened and shown to be empty, and then you have the choice to either stay or switch. So let's suppose that the money just happens to be in door number 612. Why not? So this door has the money. Now, at the beginning, you are just choosing at random from 1,000 doors. You're quite unlikely to just happen to choose that door by chance. There's a 1 in 1,000 chance. So you select some other door. Let's say you happen to pick door 430. Then every door except for 612 and 430 is opened, and you know that they're all empty. Then you have the option to switch or stay the same. And I think essentially what this should allow you to see is that by opening every door except for your door and one other door, the host is essentially pointing you to the correct door. And it seems, I think it's quite intuitive when presented this way, that the probability of you choosing correctly in the first place doesn't change by opening other doors. But there is all of the probabilities do get allotted to the door the only other door which wasn't opened. So in this case, it's very obvious that you want to switch because essentially opening the doors was pointing you to the correct door when there are so many doors and you're so unlikely to choose correctly in the first place. But the same logic really applies even in the 3-door case. It's just a little less obvious because you do have a 1/3 chance of guessing correctly in the first place. But again, by eliminating one of the other doors, it doesn't increase the probability that you're right in the first place. It's more like pointing you to the correct door. I hope that makes this somewhat unintuitive problem a little more clear and understandable why the probabilities change in the way they do. Thanks for watching.